we're going to go to the last story, which kind of creates a nice bookend
Yeah.
for all the fans of the new TV show on Apple TV, The Studio. We need a nice bookend. I love a good bookend. And so the last story is out of both Scientific American and CBS News. This is also sort of like a brand new breaking story.
Yeah.
Which is, again, another word, hints of atmosphere on Earth-sized exoplanets raises hopes for life. In another James Webb Space Telescope finding.
Yep.
What's interesting about this one is like Halo, they came out guns blazing, dual-wielding research papers.
Yeah.
So there wasn't one.
Yeah.
It was two in the Astrophysical Journal Letters
Yeah.
related to this hints of atmosphere. So it's sort of great that we just talked through the transit method.
Yes. Yeah.
And understanding how would JWST detect the atmosphere from using sensor technology.
Exactly, yeah.
So we have that grounding.
So we have that grounding now. And now we are looking, so this came out September 8th, very recent.
This was 2 days ago.
Everyone's excited about this because this is a paper on the TRAPPIST.
TRAPPIST-1.
TRAPPIST-1. Have you heard about this?
So TRAPPIST has been, again, because I do the UAP stuff.
Yeah.
A lot of people are
TRAPPIST-1,
that's
everybody loves.
That's where the aliens are.
That's where the aliens are. Everyone's like, that's where the aliens are, right? TRAPPIST-1 is a great little micro lab for solar system research. Okay. The reason for it is it's got a bunch of rocky planets that are all transiting.
Oh, in front of we just talked about
the sun, right? The problem with finding planets is
Yes.
it's incredibly hard to detect, right? Think about think about how we find the planets, right? You were saying that you got to look at this thing.
Yes.
You got to look at the star, and you got to look for the star's brightness to dim.
Yes.
And then you got to wait for it to dim again.
Right.
And then you have two, and you got to wait for that third because then you know that it's rhythmic.
It's rhythmic.
Right?
Right.
If it's just two, it could just be two random things going in front,
Right.
or whatever, and then so you have to wait for that.
Yes.
The other thing is you got to get lucky, right?
Right.
The solar system has to be on edge to our field of view. If you've got a star over here and the solar system is doing this,
it won't pass in front.
it's never going to pass in front, and I'm never going to see it.
Right.
Right. And so the solar system has to have that exact angle
Right.
of being in our line of sight.
Yeah.
Right.
It can't be up here, angle.
So you've got to be incredibly lucky. This thing is not only on edge,
Yeah.
right? It's got a bunch of planets
Yes.
that are all on edge,
Yes.
that are doing this transiting.
Yes.
Also, the transits are very, very short, from 1.5 days to 19 days.
This goes back to what we were talking about earlier. If there was an alien species looking at Earth, our transit time's a year.
A year. They'd have to keep staring at the sun. They'd probably see Mercury,
Right.
And then they'd be like, "Oh, there's no atmosphere on this thing,"
Right, and then give up.
and then give up, right?
And
but
they'd
then they'd see Venus and they'd be like, "That's got a hell of an atmosphere,"
Right.
But Earth, they'd have to wait 365 days.
Just for once, and then they'd have to wait 2 more years to get the 3.
Yeah, 2 more years to get all 3.
So the fact that the transit's just a couple of days.
Couple of days to 20 days.
It's huge because
huge.
It's because this is a resource allocation issue. If we had a bunch of these tools,
Yeah.
we could just point wherever or leave them forever. It doesn't matter.
Yeah.
But there's limited time, and everyone wants to look at different things for different reasons. And so that's a really good point that the transit time
Is so short.
is so short, which is a
Yeah.
meaningful variable. In
Yeah,
this.
and the other great thing is, so TRAPPIST has a bunch of these planets, right?
Yes.
So imagine you've got a star like this, and you've got a bunch of planets,
Yes.
right? Now, where the habitable zone is,
Yeah.
is kind of nebulous.
Okay.
Right? It's we don't know exactly there's no hard line
Yeah.
of that Goldilocks zone.
Yeah.
But because we've got all of these in a line, even if the habitable zone is here, there's going to be a few planets in there.
Yeah.
Even if the habitable zone is out here, there's going to be a few planets in there. So it's hedging our bets on all of these planets. Right? That's why TRAPPIST-1 is very exciting to us. It was found by the TRAPPIST system, which is this transitory planetary project in La Silla, Chile. Really quite small telescopes, to be honest, that are just doing this thing where they just stare at a bunch of stars and then try to do photometry on them to figure out brightness.
Yep.
And it found this thing, I think, in 2016, and ever since it's been a big part of the exoplanet
research community.
Yeah. So a bunch of planets have been found. As we've looked at it for longer and longer, we know that some of these inner planets do not have an atmosphere.
Okay.
Okay. it makes sense because this solar system is extremely small.
It's like condensed.
It's condensed.
Yeah.
The star itself is an M dwarf.
Okay.
The classification of stars goes O, B, A, F, G, K, M. We are a G-type star, the sun.
Yep.
M is all the way on the right-hand side of the Hertzsprung-Russell diagram. It's tiny. It's red. It's tiny.
Yeah.
Okay. And so this entire planetary system is condensed inside of the orbit of Mercury.
Oh, wow. Wow. So the distance between our sun and Mercury.
Yeah.
All
of these planets
are
inside there. Okay. Now, that's a good thing because if you've got a really dim star, you want to be close to it in order to like have liquid water and all this other kind of stuff. On the other hand, if you're that close to a star, the star is going to act up.
Right.
Right. There's going to be solar flares.
Yep.
There's going to be random like it's going to like vomit.
Yes.
And then you just get a giant dose of radiation.
Right.
Right. So that's probably why the inner planets don't have an atmosphere anymore because like you're too close to the star. Like even though the star is like small, it's still going to be volatile. It's still going to have all these like little outbursts, and so you're kind of screwed there. But the TRAPPIST-1e, which is E is the planet.
Yes.
Now this is, I believe, the fourth planet that's out there. That's something that is kind of Earth-like.
Yes.
Okay. It's about 90% the radius of the Earth, so
Okay.
about 60% the mass.
Yeah.
Which means it's like, if we're on there, we can like at least like hang out.
Yeah.
We'd be jumping a little bit higher.
A little moon-like.
Yeah, a little moon-like-ish, but it's not like something that is completely foreign to us.
Okay.
Right?
Yeah.
The moon is a sixth of Earth's gravity. This is, gonna be like 60%.
It's like a trampoline world.
Yeah. And it's got an equilibrium temperature, they say, of about 250 Kelvin. Okay, so it's a little bit out of where the Earth would be to get Earth's equilibrium temperature, which is around like 280 Kelvin. This is at 250 Kelvin, which is negative 20 degrees Celsius.
Okay.
That's the equilibrium temperature. Now, the thing is, you can have, if you've got an atmosphere like Venus, you can have a massive greenhouse effect.
Okay.
And then that greenhouse effect can keep
heat in.
And if you have a massive greenhouse effect, the pressure is also higher. So then you can have liquid water, right? So there's a possibility that we could have liquid water on this thing, and we could have types of habitable like qualities on this thing, right? So trying to figure this out is a big problem. Okay. The other cool thing about all of these planets are because they're so close to their sun.
Yes.
Right. They're within the orbit of Mercury.
Yes.
Right. They do this thing called tidal locking, which is something that the Mercury does to the sun and something that the moon does to the Earth.
Yes.
Whenever we look at the moon, we see the same face of the moon.
Right.
And that's because as it rotates, it's also rotating itself.
Yes.
Right. And the rate of rotation is matching the rate at which it rotates the Earth.
Yeah.
Right? The Earth doesn't do that, right? The
Right.
Earth spins once every 24 hours.
Yeah.
Once a day.
Yeah.
And then it takes 365 days to go all the way around. That's why we have 365 days. A day on the moon is also a year on the moon if the Earth is like kind of its center. You know what I mean?
I know what
a day on Mercury is also a year on Mercury.
Yeah.
Right?
Yeah.
All of these planets, because they're so close to the sun, they also
locked.
have this tidal locking, right? Which means they also always face their sun.
The point is there's one side of the rock is always in the sun.
And the other side is always
in the dark. This is why when people say the dark side of the moon, we never see the dark side of the moon. The Chinese can because they landed something and they're over there and we don't know what they're doing. And the national security state is freaking out about that.
Yeah, it's freaking out. Yeah.
But that's as like.
But that's the idea.
That's the idea.
That's the idea. Yeah. So like, that actually causes some problems for like, because the Earth has this dynamic climate. A lot of it is because we've got all parts of the Earth getting some sunlight, right? Now imagine like you've got something like this. What kind of world would that be?
Right.
And I was reading about this. It's really cool. They call it the staring eyeball planet.
Okay.
Okay. So what's happening is you've got one part of the planet looking at the sun, right?
Yes.
If this thing is really cold,
Yeah.
then okay, fine. The dark side is just going to be frozen.
Yeah.
But the part that's looking at the sun, there's going to be a central part that is sort of hot.
Yeah.
And like maybe has liquid water if it has water.
Yeah.
And then as you go towards the outer parts, you're going to have this middle region where it's like freezing.
Yeah.
And so you're going to have this eyeball staring at that sun the whole time, right?
Yep.
Where the central part that is where the sun is always overhead all the time.
Yes.
That's going to be the part that's going to be where
you want to
there's
look.
going to be this temperate zone, right?
Yep.
Where we would want to live if we ever went there.
Yep.
Which is kind of cool to think about, like a planet that looks like a staring eyeball.
Yeah.
Anyways, so they're trying to find the atmosphere on this thing.
Right.
Okay. So you want to do the same thing that you did with the K218b.
Yes.
Right. You want to look at this thing. You want to look at the star on its own. Then you want to look at the planet transiting it, and you want to see which wavelengths does the atmosphere, if it has one, absorb. Okay. If it had no atmosphere, every single wavelength would be absorbed at exactly the same amount, and you would just have a flat line, no barcode,
flat
right?
tip. Yep.
No barcode, just flat absorption across the spectrum.
Right.
Okay.
To take the bar, just to like really emphasize the barcode analogy, it would be like just having a barcode where all the bars are exactly the same. Like some barcodes like have a little like jigger pattern and this and that, but it would just be like no.
It would just be black.
Yes. Yeah.
There would be no
yeah.
white black markings. Right.
Right.
Yeah. So it would just there would be no barcode.
That's the no atmosphere barcode.
Yeah, that's the no atmosphere barcode. Okay. So they get data from 4 transits because again this thing 20 days.
Yeah.
So quick. We're like, all right, let's just stare at it.
Right.
They get this thing for 4 different transits, and what you want to do is you want to average them out so that you get like higher signal to noise, right? And it was weird.
Okay.
Because the first 2 times, the transits look way different than the next 2 times. Okay, and that's very strange.
Would it be especially strange, like because it's tidally locked? That would mean we would get, in theory, some more semblance of consistency.
Yeah, because you're getting that same slice, right?
Every
the same
time.
slice every time. And you're thinking that there's not a lot of circulation because this thing is so tidally locked, right? There's not like the thing isn't like revolving underneath where there's like mixing and stuff going on.
Right.
So you would expect that the atmosphere, the atmospheric signature should be static.
Right.
Okay? This is not. So what's happening here? And it turns out that the star itself is pretty volatile.
Okay.
Okay? And so when it's like if the star has, let's say, like a sunspot on it at some point, and then I do a transit versus when the star is just like a normal star. It doesn't have a flare, right? Then you're going to get these different the initial background radiation has signatures that then are getting confounded by the thing in front.
Yep.
Right? And that's why this thing required 2 papers.
I see.
Okay. So the first paper, which is by Espinosa and the colleagues, that one was trying to mitigate something called stellar contamination. Okay. That's the idea of, how do we model the starlight and try to get a clean spectrum out?
It's basically, we want to remove the star's radiation effects. Like, how do we get rid of that noise to get just the planet's atmospheric barcode?
And so that was the Espinosa paper.
Okay.
Then there's the Glidden paper.
Yes.
And that one does a detailed analysis of the spectrum that comes out of the Espinosa paper.
So someone created a model to get rid of the radiation.
So there's a techniques paper.
And
then there's a paper about now that the technique, because the technique already to do this. Required so much stuff that they're like, this needs to be its own thing. I need a first author on this. All right.
I love
research. Make me a minor author on the other one, but this one I got a career to think about. But it's a really cool way of doing things. They did this again. It's a probabilistic framework.
Right.
They did this thing called Gaussian processes. Okay, which is basically like. It's a probabilistic solution where what you're doing is you're like varying all these functions on all the things that the stars could be and like what you're seeing, and then you try to match. And then you try to get like a sort of single combined decontaminated transmission spectrum out, right, of that TRAPPIST 1E.
So the idea is we were originally just getting this like initial barcode that included the contamination.
Yeah, from the star,
from
just
the star.
doing weird stuff.
So now we have like a remixed barcode.
Yeah, to try to get that static atmosphere out.
Just the atmosphere.
Yeah, out of those 4 transits.
So if it's like we wanted a it's like a rap song. It's like no features.
Yeah,
this is the J. Cole album.
Yeah,
we just want J. Cole.
Yep.
No features.
No features, exactly. But you're giving me
we got Young Thug, we got Drake, we got all those other people here, and then I just want J. Cole.
I just want J. Cole. So once they got J. Cole, then the J. Cole went to the Glidden team, and then they're the ones who are like, okay, this is what J. Cole's like.
Yeah, right. Okay, yep. Okay.
Yeah, so the Glidden team then gets this atmosphere out, which is this decontaminated spectrum, and from that they do some analysis. So again, they're going to do the same thing where they have this atmospheric Bayesian retrieval, where they're going to try and fit all these atmospheres. One of the other cool things they did was actually, one of them is this model agnostic. So before even involving the model and like trying to fit like all these different models, they just did like a fundamental physics type of thing, which is like, let's try to figure out how big the molecules are.
Okay.
In atomic units. Atomic units are basically like 1 proton, 1 neutron, okay? So like hydrogen would have a molecular weight of 2 because there's 1 proton, 1 proton, right. H2, right? Oxygen would have a molecular weight of 32 because it's 16 and 16. 8 protons, 8 neutrons, 8 protons, 8 neutrons to make the O2 molecule. CO2 would be even more. That would be 32 plus 12, which is 44, right? So one can figure out the molecular weight of that atmosphere by modeling the height of the atmosphere, okay? Because if the dominant gas, let's say the dominant gas is of some molecular weight, the higher the molecular weight, the lower the atmosphere is going to be, because it's heavier, right? Also, we know the temperature, right? The higher the temperature, the higher the atmosphere is going to be because there's going to be more energy for it to go higher. Also, the higher gravity is, the lower the atmosphere is. But the gravity we can kind of tell based on the density metrics to be like, okay, it's about 60% of Earth. Temperature we can tell based on its distance from the thing, so we can say it's 250 Kelvin. And then the height we can tell by looking at the way that this transit works. Right. By the way that the transit works. And so now we can fit the molecular species. And they found that the lower bound on the molecular weight is about 9 molecular units. Crucially, that means it can't be hydrogen. And that's huge. Okay. If it's not a hydrogen-dominated atmosphere, that's a very good thing because that means you've got higher pressures, you've got potentially greenhouse effects going on, right? And you've already just from fundamental physics ruled out that there's probably not hydrogen there. So it's not like one of these Jupiters, right? Jupiter is just like all hydrogen, effectively, like a bunch of helium.
That's so clever.
It's a nice one, right?
No, I thought that was cool. No, that's really, and again, it's sometimes. I keep coming back to this point every time we talk about these experimental designs is like sometimes it's just about reframing the problem set. Right? It's not necessarily that you need the new shiny thing. Sometimes you have the data and you just need to kind of come at it at a different entry point, and then your follow-ons. Because now I know you're going to continue. So now that we know that, like, it creates a different context by which you're then analyzing all the other downstream steps in the process.
Yeah. So now you can start simulating atmospheres that don't have hydrogen, right?
Which removes a whole.
And so then so what they did was they simulated a bunch of atmospheres. What they're figuring out is there's probably also not a lot of CO2. Okay. Which means that it's not like Mars or Venus. Venus and Mars are basically all CO2. So this one's not like Venus or Mars. They say at this point what they're saying is it's either it's got no atmosphere and we're seeing just noise, or it's got an atmosphere, not hydrogen, not CO2, but perhaps a lot of nitrogen, kind of like the Earth, also kind of like Titan, and it's got signatures of a lot of methane. We don't see a lot of oxygen, I don't think. Okay. So there's no like photosynthesis going on, which kind of makes sense. I mean, the star is so dim.
It's not a big enough power source.
I mean, if it was doing photosynthesis, perhaps it's doing a much different kind of photosynthesis because the spectrum of the star is so different from the sun's, right?
Sure.
But nitrogen and methane, which is kind of like Titan, which is very exciting because Titan is also a candidate for, potential life.
Tantalizing signs,
right? And so it also gives credence to like perhaps studying Titan a bit more, right? To see if worlds like Titan are very common in the galaxy, then studying Titan more is going to give us more clues into how this would work. Right.
And Titan's closer. The point is, it's closer. We can do more there, and then we can extrapolate what we learned from that to farther.
Exactly. Yeah. And so that's the whole idea. I mean, they're looking forward to more transits in the future, and actually, what they're going to do that's kind of really cool is they're going to see what a transit on the B planet looks like, because the B planet doesn't have any atmosphere. We know that for sure, right? And so then, if we can figure out what a transit for B looks like and just like get a bunch of that data, then we can model the star transiting a bare rock really well, and then we can have an even better idea on what the transit on the E planet would look like, right? And then we get better data, better signal to noise, better model fitting, higher confidence on whatever's out there.
We need to do Alien Week like Shark Week on the pod.
Every once in a while, whenever there's something cool, like we got to do it.
I mean, literally,
this one was cool, right? The Mars story is very cool.
This week we had not only this hint of atmosphere on Earth-sized exoplanets, which came out 2 days ago on September 8th. We also had the NASA announcement, totally separate, totally different context for Mars.
And all four stories are American.
Yeah, look,
right?
Look, you can't avoid us.
You can't avoid us, right? The Mars story is obviously the Perseverance rover and JPL, and then the other three papers, all James Webb, baby.
James Webb, which again, this is why we need to continue to fund science. If you want aliens, we have to fund the fundamental research.
Yeah, even if the aliens are looking at us, right? And we give up on science.
Yeah, they're gonna be like,
man, they almost had us.
They almost had us. They almost had us.